Uh, Good morning to all of you. Am I audible to all of you?
Yes, sir.
Okay. So still our number is less, but we have to continue the class as the part may not cover. So now I am going to present about the block 3, the second and third law of thermodynamics. Okay. Second and third laws of thermodynamics. It is block T. It, it contains 4 units. In first unit, that is unit 8, we will discuss about the Carnot cycle, Carnot engine, refrigerator, second law of thermodynamics, etc. So before going to Carnot cycle, we learn about the heat engine. What is the role of heat engine? It converts heat into work. How can we convert heat into work? It needs an engine. And the heat engine, the basic components of the heat engine, they are the source or a hot reservoir, a sink, a cold reservoir. That means the reservoir, hot reservoir is at a higher temperature, cold reservoir is at low temperature. And engine, the which takes heat from the hot reservoir or source, does some work and rejects some amount of heat to the sink. So we will later on discuss whether the engine can draw the heat from the source and uh, completely convert into the work. So heat engine operates between two heat reservoirs. One is hot reservoir, other one is cold reservoir. And to measure the efficiency, how the engine works, the efficiency, since the work of the engine to convert heat into work, so how much useful work is done out of the heat absorbed. So efficiency symbol is eta. It is useful work done by heat absorbed. Useful work is how much heat is converted into work, right? The work W equal to, suppose you take Q1 heat from the source and rejects Q2 heat into the sink, then the amount of heat which is converted into work is Q1 minus Q2. Q1 minus Q2 divided by the heat receives from the source, that is Q1. If divide, that will becomes 1 minus Q2 by Q1. So we know that heat engine, for heat engine, two reservoirs are required. And what is the actually the form of the engine? It is a barrel, cylindrical barrel shape, fitted with a frictionless piston. So frictionless piston, and it contains some gas. We may say it is ideal gas, which is known as working substance. Actually, gas does the work. the Carnot cycle. Carnot cycle operates with 4 steps and the different components of the Carnot cycle are the source, which is at a higher temperature, T1 Kelvin say, a sink, a body at low temperature, T2 Kelvin shape, then engine, you see this is the barrel and this is the piston. This is the piston. This frictionless piston contains some gas and its lower part is conducting, the other sides are insulating. So, this engine can exchange heat with the source or sink or the surrounding through this side, the bottom side. Bottom side is conducting. Another requirement is insulating stand. Actually, this Carnot cycle is a theoretical engine. We will discuss later. These 4 steps are, you see, the isothermal expansion, 1, adiabatic expansion of the working substance. This working substance contained in the engine, then isothermal compression and adiabatic compression. Okay. Now see, suppose the gas, ideal gas contained in the barrel is at pressure P1, volume V1, temperature T1. This, when the isothermal expansion takes place, how we do? Now first the engine is placed over the source and the barrel is moved upward so that gas expands. So when the gas expands, its temperature will fall, but since it is placed on the source, the heat is absorbed from the source to keep the temperature of the gas constant. Since here expansion undergoes at constant temperature, so this is isothermal expansion. In isothermal expansion, pressure volume changes at constant temperature. So the system or gas goes from P1 V1 T1, the initial, to P2 V2. Pressure volume changes, but the temperature remains constant. So it is isothermal expansion. In the next step, this barrel is placed over the insulating stand. Now see, when it is placed over the insulating stand, this gas is completely insulated from the surrounding. So its bottom is conducting, but it is placed on over the insulating stand. Okay, the insulating, so this becomes insulated from the surrounding. So instead, now if you further move the piston upward, the gas will again expand, but the heat cannot be taken from outside. So the temperature of the gas falls. That means in this case, the expansion takes place. When expansion takes place, volume increases, pressure decreases, but the temperature does not remain constant, as we cannot draw heat, but the gas cannot draw heat from the outside. So this is an adiabatic expansion. In this case, the pressure, now see, this is the second stage. When second stage starts, the pressure, volume and temperature of the gas was P2, V2, T1, right? P2, V2, T1, and it changes to P3, V3, T2, P3, V3, T2. Okay, so uh, this is known as adiabatic expansion. Okay, next we will place the barrel over the sink. Now, when we place the barrel over the sink, now compression start. That means the barrel is moved downward so that gas compresses and the volume increases, pressure increases, and temperature also increases. But the heat is rejected to the sink so that the temperature of the gas remains constant. Hence, the pressure volume situation from changes from P3 V3 T2 to P4 V4 T2. Now see, pressure volume changes but temperature remains constant. So this is a case of isothermal compression. Isothermal compression. Okay. Now, when in the next step the barrel is placed over the insulating stand. So we have placed the barrel over the insulating stand twice. Okay, we have to place the barrel twice in the insulating stand. So when the barrel is placed insulating over the insulating stand, the bottom end is insulated now. Now again we compress the piston, that is it moves downward. When piston is moved downward, the gas compresses and uh, uh, and the pressure volume changes from P4 V4 T2 to P1 V1 T1. This is the initial state. So we slowly compresses the piston so that the gas will reach, that is the working substance will reach or system will reach the initial state. That is why we say this is a Carnot reversible cycle. Then after performance of so many steps, the working substance comes back to its initial state. Its initial state was P1, B1, T1. Now after completion of 4 steps, the ideal the working substance or gas is at pressure P1, B1, T1. So reversible cycle. In every case, we will find the what is work done. In the isothermal expansion, what is the expression of work done? In adiabatic expansion, what is the work done? In compression, what is the work done? And adiabatic compression, what is the work done? We know the expression of the work done in case of isothermal expansion or compression. Isothermal expansion, in that case, the work done is positive, and adiabatic expansion work done positive, and in these two cases work done are negative. So we can calculate the total work done in the 4 processes. We have to add the 4 works: W1 for isothermal expansion, W2 for adiabatic expansion, W3 for isothermal compression, and W4 for adiabatic compression. Right? So this is the we can calculate the work done. Then we'll derive expression for efficiency. Efficiency we know eta equal to 1 minus, this will come out to be efficiency W equal efficiency eta equal to W by Q1, and we will find that W equal to Q1 minus Q2 by Q1, that becomes 1 minus Q2 by Q1, Q1 minus Q2 by Q1. So exactly this it will come like this, W equal to Q1 minus Q2 by Q1. So 1 minus Q2 by Q1, and this is same as equal to 1 minus T2 by T1. That is the temperature of the source and the temperature of the sink T2 and temperature of the source T1. Shilpa, Shilpa, am I audible?
Yes, sir.
Why do so late?
Sir, I have some work, so finishing and attend the class.
Okay, okay, okay.
Yes, sir.
Okay, okay, mute your microphone. Now see, from the efficiency, expression of efficiency, what we know, efficiency eta equal to 1 minus Q2 by Q1 equal to 1 minus T2 by T1. If we compare these two expressions, we can write also Q2 by Q1 equal to T2 by T1. Okay, now see, efficiency depends on temperature difference, not on the nature of working substance. Nature of working substance means the ideal gas taken in the barrel. So it doesn't depend upon the nature of the gas. It only depends upon the temperature difference, that is the temperature of source and temperature of the sink. Now see, if T2 is 0, that means sink at absolute 0, then efficiency equal to 1. Actually, this is not possible. Okay, since T2 cannot be 0, T2 by T1, that will come as a proper fraction. Of course, it is less than 1. So when a proper fraction is subtracted from 1, the value must be less than 1. So that is why eta is generally less than 1.
ସାର୍ ଟିକେ ସ୍କ୍ରିନ୍ ବଡ଼ କଲେ ଦେଖାଯିବ, କିଛି ଦେଖାଯାଉନି ସାର୍, ସେଥିପାଇଁ ବୁଝା ପଡ଼ୁନି।
ସ୍କ୍ରିନ୍ ବଡ଼ କରିଦେ, ଦେଖାଗଲା କି?
ନା ସାର୍।
ମୁଁ ତ ବହୁତ ମ୍ୟାଗ୍ନିଫାଇ କରିଦେଲି।
ସାର୍ ଜୁମ୍ କଲେ ଦେଖାଯିବ ବୋଧେ।
ଜୁମ୍ କରୁଛି, ଜୁମ୍ କରିସାରିଲିଣି। ଆହୁରି ଜୁମ୍ ହବ, ଦେଖନି।
ହଁ ସାର୍, ହଁ ସାର୍,
ଆସିଲା?
ହଁ ଏଥର ହେଲା ସାର୍, ଏଥର।
ଓକେ ଓକେ ଓକେ। efficiency ଦେଖ, efficiency ର expression is very important, because from this expression of efficiency cycle we derive second law of thermodynamics. Okay, efficiency କଣ କହୁଛି? efficiency कहूची जे it only depends तामने efficiency कौन कहूची जे how much heat is converted into work. If we compare two machines, two machines draws equal amount of heat, but one machine does more work, other machine does less work. Then which machine will be more effective? The machine which does more work from same heat. The efficiency is very important for us. Always we try to develop an engine which is more efficient, which will be more efficient. Efficiency depends upon the temperature difference, that is temperature of source and temperature of sink. Okay, and not upon the nature of the working substance. Say whatever ideal gas you choose, the efficiency will not vary with the gas which it only depends on the temperature of the source and temperature of the sink. Now, value of eta will be less than 1 and eta becomes 0. Eta becomes 0. If T2 equal to T1. T2 equal to T1 means the temperature of the source and temperature of the sink are same. So then efficiency of the engine becomes 0. So we can say engine cannot be operated if efficiency 0, no work is done. Then what is the necessity of engine? So engine cannot be operated without temperature difference. Without temperature difference, it cannot work. Another thing I also forgot to write here, that is T2. If T2 equal to 0, eta equal to 1. When T2 equal to 0, eta equal to 1. Similarly, Q2 equal to 0. That means no heat is rejected to the sink. Actually, absolute 0 is not practically possible. Why? Now, at absolute 0 temperature, we learn from the kinetic theory that the molecular motion ceases. Molecule motion re rahibe nahi. 1. Second, its pressure 0, its volume 0. Can you take gas molecules and we make its volume, their volume 0? Not possible. Not possible. So absolute 0 is not possible. That is a mathematical after or thinking that is not practically possible. Why? If you can, we can mathematically think about it, because when we lower the temperature of a substance or temperature of the system, the temperature you can make it 0, not negative. Negative doesn't have any physical significance. So we can make a temperature 0 up to 0 level. But that is not practical possible, because at absolute 0, no gas has volume, pressure, no molecular motion. So actually this is not, that is why it is not possible. Since absolute 0 is not possible, T2 cannot be 0, then efficiency cannot be 1. If efficiency cannot be 1, then you have to reject some to the sink. That is why for a heat engine, the two things are required. One is a reservoir at higher temperature and another should be at lower temperature. Okay. Now see, Carnot cycle as a refrigerator. Everyone, we have a refrigerator in the household. Now see how Carnot cycle becomes refrigerator. If Carnot cycle working in the reverse direction means we are drawing heat from the source and rejecting heat to the sink. The process will be and does some external work by the gas. The gas মানে ideal gas যাকে আমি কହୁଛେ working substance. The working substance will draw heat from the source, does some work and reject the rest heat the surrounding जो sink. So in this case you have to draw heat due to reverse way. That means heat can be received from the sink. Q2 heat will be received from sink and some work will be done on the externally work will be done on the working substance. On the substance, not here by the working substance, work will be done not by the working substance, work will be done from the outside, external agency will do work W. So Q2 heat is drawn from the sink, external work is W on the refrigerator and heat rejected Q1 to the sink source. So Q1 equal to W plus Q2 for conservation of energy. Q2 is taken here, W work is done on the gas or working substance. So Q1 heat will be rejected to the source. That we write here also. Heat Q2 absorbed by the working substance from the sink, work done on the system and Q1 heat is rejected to the source. In this case, we define a term coefficient of performance or fit merit of refrigerator, and that is defined as heat extracted from the sink. How much heat extracted from the sink and what work is done externally, that is work input. So to draw Q2 amount of heat, how much work is done by the external agency. So Q2 by W, and we know W equal to Q1 minus Q2, since Q1 equal to W plus Q2. So W equal to Q1 minus Q2, and you can write also this is equal to T2 by T1 minus T2 or 1 by T1 by T2 minus 1. Now we go for the second law of thermodynamics. Now some drawbacks are there for first law of thermodynamics. So what are the drawbacks and what is the first law of thermodynamics? So if heat given to a system and it does some work W, then heat equal to the change in internal energy of the system plus work done. Now first question is, can we supply heat to every system? That means suppose you are at lower temperature and the system is at higher temperature. Can you supply heat? The first question. The first law is silent about that. It doesn't say anything about that. So we write drawback is direction.
Sir,
Tell me. Okay.
sir,
Okay.
sir, can we
Direction
write
of
this?
heat.
Can we write this topic, sir?
Hmm. Can you write this topic?
The second law of thermodynamics.
Huh. कौन टॉपिक लिखिबा माने कौन कहू
आमे लेखि पारिबो कि सर?
हां काई लिखि परिबो
सर टिके देखा जाउनी माने तळକୁ आसियो तार सबु थियोरी गुडा देखा जाउनी हैला सर
हैला बे
हां सर
हां आगे बुझु मु पठै देबी तम पाखु किछ कथा नै जे हला बुझ आगे भलो कि बुझ कारण तुमको येटा मिलु नै कौन जो मटेरियल कलेक्ट कलनी स्टडी मटेरियल
नो सर ओनली सॉफ्ट कॉपी द ये ऑनलाइन रे अच्छी पीडीएफ
हां 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 सॉफ्ट
ई
कॉपी
ज्ञान कोश
हां ठीक है ओके देखो डायरेक्शन ऑफ नहीं आ जने पचारथिले डायरेक्शन ऑफ हीट फ्लो कथाटा कोन टिके रह से जे पचारथिले से पचार डायरेक्शन ऑफ हीट फ्लो टा जानि परछ ना नहीं डायरेक्शन ऑफ हीट फ्लो कहिले हीट को डायरेक्शन रे फ्लो हबो फर्स्ट लॉ ऑफ thermodynamics is silent first law of thermodynamics कहला if some heat is given to a system and it does some work and its internal energy changes then heat equal to change in internal energy plus work done that is this is nothing but the conservation of energy principle of conservation of energy if we given some energy to a system energy cannot be created cannot nor be destroyed so neither created nor destroyed it can only transfer from one form to another suppose we give some heat in one that is one form of energy what it does now it changes internal energy and does some work so the work and internal energy they together should be equal to the supplied heat this is conservation of energy nothing but it doesn't say whether you can you can supply heat to a system or not that means suppose you are at lower temperature the system is at higher temperature can we flow the heat no but it is not the first law is silent about that second how much heat will be converted into work suppose you supply q amount of heat and you say there is change in internal energy plus work done if internal energy will not change that means total heat can be converted into work if total heat can be converted into work then efficiency equal to 1 if efficiency equal to 1 what we derive from the Carnot cycle if efficiency is 1 then the either the source temperature should be 0 absolute 0 but this absolute 0 is not possible absolute 0 is not possible that is why the efficiency cannot be 100% efficiency is not possible that may be a theoretical perception that we say this how we consider that the piston is frictionless can you make a frictionless piston completely there must be some friction maybe it is very small this is theoretically we can think of 100% efficiency but practically this is not possible that we discuss so efficiency now see if efficiency is 1 then it is absolute 0 is since absolute 0 is not possible efficiency cannot be 1 it is less than 1 so if efficiency is less than 1 what we can say that total heat supplied to a system cannot be converted into work if it is can be converted into work cannot be converted into work then how much it will be converted into work about this the first law is silent so these are the drawbacks of the first law of thermodynamics and this is overcome by the second law of thermodynamics so how second law of thermodynamics Second law of thermodynamics is stated by we have two statements, that is Kelvin-Planck statement and Class statement. Both these statements are equivalent. They appear to be different, but they are equivalent. Now see what Kelvin-Planck statement says. No process is possible whose sole result is complete conversion of heat into work. Okay, that means you cannot convert total heat into work. That is why efficiency is not 1, it is less than 1. Okay, this is 1. Efficiency cannot be 1. If efficiency cannot be 1, so you must have the two sources, that is two reservoirs. One is the source, higher hot reservoir, another should be low reservoir, because without temperature difference, the engine cannot perform. Temperature difference is must. Is temperature difference is must. One must be higher temperature, or should be lower temperature. Temperature difference means not temperatures are not equal. If they are not equal, then someone must be greater, someone must be lower. So the two temperatures T1 and T2 required. One thing. Okay. Second thing is the class statement. This class statement says no process is possible whose sole result is the transfer of heat from a body at a low temperature to a body at a higher temperature. Okay, so this statement is relevant for working of refrigerator. That means it fixes the direction of heat flow. So you cannot transfer heat from a body at lower temperature to a body at higher temperature. But we do that in a refrigerator. How? With the help of external agency. So heat cannot flow automatically from lower body, low temperature body to a higher temperature body. Net heat flow will not be done from low temperature body to higher temperature body. And when it is possible, if an external agency do some work to draw heat from the lower temperature and reject it into the higher temperature body. That we do, that happens in case of refrigerator. In case of refrigerator, what we do? Now we keep substances inside the refrigerator. Now see, when the refrigerator, before the refrigerator starts operating, what we observe, that both are, suppose you take a substance and place inside the refrigerator. So before placing, it was at the surrounding, and its temperature must equal to the surrounding temperature, same. But after some time, you find when the refrigerator operates, the temperature of the substance inside the refrigerator falls down. That means so how? Now the heat is drawn from the body inside the refrigerator and it is rejected to the surrounding, and that is possible because of the electrical energy used. So without electrical energy, can you operate the refrigerator? No. So here external agency is the electrical energy. Electrical energy. So it draws it from the body inside the refrigerator, which is at low temperature. And once it remains cool means, and as long as the refrigerator is working, the substance is more and more cooler. That means we are continuously drawing heat from the lower temperature body and rejecting it to the surrounding which is at a higher temperature. Okay, so it cannot be flown. Now another thing is, it is the second law of thermodynamics, Carnot theorem. Carnot theorem says about the what is the statement? It states that of all heat engines working between the same temperatures, all heat engine working between the same temperatures, the reversible Carnot engine has the maximum efficiency. That means you take two heat engines, one is reversible heat engine, another is irreversible heat engine. That means reversible heat engine, Carnot engine, reversible Carnot engine, say the initial state after one of the steps, 4 steps, you see the initial state and final state of the working substance is same. That is, but in case of irreversible, so the final initial may not be same. Okay. So Carnot theorem says that the Carnot engine has more efficiency than all other irreversible heat engines, because Carnot engine is we consider here many things which is not actually theoretically ideal, but practically that is not possible. That is why the efficiency of Carnot engine is greater than all heat engines. You can verify show it. Now next unit we go for entropy and laws of thermodynamics. Now see how the entropy is defined. Entropy is defined as, you see lesson ds. S is the symbol for entropy. The change in entropy is the change in the supplied heat, the infinitesimal heat supplied delta Q in reversible condition. Delta Q heat is supplied in reversible condition at temperature T, constant temperature T. Okay. Then the change in entropy, the S, the D symbol is used for change. ds, S is the entropy, ds equal delta Q reversible by temperature. So we write it, that is when we add an infinitesimal amount of heat delta Q reversible to a system at constant temperature T, its entropy increases by delta Q reversible by T. Say either increase or decrease, that is the change. So change in entropy is delta Q reversible by T. Now see, entropy is an extensive variable that it doesn't depend upon the mass. Extensive variable doesn't depend upon the mass and is a state function. We will find the expression of entropy for ideal gas. We will see that depends upon the initial and final temperatures, initial final volumes or pressures. So that is a state function, because the state of a system are represented by these variables: pressure, volume, temperature, internal energy, so and so. So entropy is an extensive variable and a state function. Now see, entropy is a mathematical tool. This is an abstract property and cannot be measured like temperature, pressure, volume. This is very important. The entropy is a mathematical tool and Since it is an abstract property, it cannot be measured like temperature. Entropy is a measure of disorder in the system. If you say if you say the system has more entropy, that means system is more disorder. So if it is more disorder, then the system has more entropy. Now go for second law of thermodynamics. You see, the second law of thermodynamics is, is it is essentially a principle of increase of entropy. And it states that when a closed system undergoes a change, its entropy cannot decrease. So when a closed system changes, its entropy cannot decrease. It either increases or remains constant. And we can mathematically write that is the delta S change than 0. When change is greater than 0, entropy increases. Change final minus initial. Final minus initial is positive, means final is greater than initial. Then entropy increases. And when it is equal to 0, that means entropy remains constant. Final equal to initial. Final minus initial equal to 0. So the greater the entropy than 0 for irreversible process. And reversible process, the entropy remains constant because it is a state function. When the initial final state are same, it depends upon the initial final. Okay. Now with the entropy change of an ideal gas of n moles, that is calculated. Now see, we write the expression. We write the expression of the change in entropy for ideal gas of n moles. What is n moles? Delta S equal to indifferent force with temperature, volume, and temperature, pressure, volume, pressure. So the expressions are different way written. NCV. Now see, first expressed in temperature and volume. NCV logarithmic of exponential base T2 by T1. ln ସେଥିପାଇଁ ଲେଖା ହେଇଛି ln T2 by T1 plus nr, r is the gas constant, ln V2 by V1. That means the change in entropy depends upon the initial final temperature and initial final volume. That is why it is a state function. Similarly, if you want to write in terms of volume and pressure, NCP, CP ହେଉଛି specific heat at constant pressure, molar specific heat at constant pressure, ln V2 by V1 plus NCV ln P2 by P1. Similarly, the in terms of temperature and pressure, NCP, the ln T2 by T1 minus nr ln P2 by P1. Entropy of phase transition. So the phase transition takes place when we know the matter exists in three states: solid, liquid, and gaseous state. Other states are also there, no? The fourth state, fifth state, no? But generally we observe the three states: solid, liquid, gaseous state. So when a substance transfers from or converts from a solid state to liquid state, this is called phase transition. Then a solid phase to liquid phase to gas phase, or solid to gaseous phase. So when solid converts to the liquid, we say the process is fusion. If we apply heat to the solid, its temperature go on increasing, and at a certain temperature and pressure, it starts melting. Once it starts melting, its temperature doesn't change. We say the fusion starts. So how much is required for fusion of the substance? So delta H fusion says molar enthalpy of fusion. Enthalpy says the total energy supplied for fusion. And the T fusion means this is the melting point. And once melting point reach, the substance starts melting and the temperature doesn't change. When the phase transition takes place, during that time there will be no change in temperature. You see, what is the melting point of ice? Who can say what is the melting point of ice? Anybody? Nobody knows what is melting point of ice.
0 degree Celsius.
0 degrees Celsius. Suppose ice is at minus 5 degrees centigrade. Then can you find the water on the ice? No, we cannot find.
No.
No, find. Now you supply heat to the ice. So what will happen? The temperature of the ice will increase from minus 5 to till 0. So once 0 degrees centigrade is reached, then ice starts melting. You find that temperature of ice will not change till whole ice gets converted into water. କେବେ observe ଜାଣିଛ? Observe କରିଛ? Observe କରିବ. When temperature will increase, when total ice is converted into water, then if you are supplying the heat, then the temperature of water will increase. Okay. Then temperature of water, suppose you go on applying heat. So if you are going applying heat, then the temperature of water will increase. How long it will increase? The temperature of water will increase up to 100 degrees Celsius. So once the 100 Celsius will reach, the water starts boiling. We say that is the vaporization process. And the temperature of the water will not change, remains at 100 degrees till total water becomes vapor. Now see, but you see the melting point of ice 0 degrees centigrade or boiling point of water is 100 degrees centigrade. We say with pressure, with standard pressure, normal pressure. Normal pressure is 76 cm of mercury or 760 mm of mercury column. If pressure will change, the melting point will change. We will not discuss about this here. If you are interested, go through it. You will learn many things. So similarly, delta S evaporation equal to delta H vaporization plus by T vaporization. So delta H vaporization is the molar enthalpy of vaporization, since the T vaporization is the boiling. Now, if you want to combine the first law and second law of thermodynamics, how it comes? Now see, the first law of thermodynamics is del Q equal to du plus dw. Supplied heat equal to change in internal energy plus work done. We know the ds equal to del Q by T. ds equal to del Q by T. So del Q equal to TdS, cross multiplication. Del Q equal del S equal to del Q by T. You make a cross multiplication. So TdS, del Q equal to TdS. and du, change in internal energy, equal to NCV dt. We know Cv is the molar specific heat at constant volume. It needs the amount of heat required to increase temperature by 1 degree centigrade of 1 mole. If you have n mole, then you have to NCV, and if temperature changes by dt, because internal change in internal energy uh, is measured by the change in temperature. So dt, then amount of heat required to change internal energy, that is NCV dt. ଜାଣିପାରୁଛ Cv ହଉଛି 1 mole, 1 mole 1 degree centigrade, ତାପରେ n mole 1 degree centigrade, NCV, n mole dt temperature, NCV into dt, 1 degree ପାଇଁ NCV, dt temperature ପାଇଁ into dt, ତେଣୁ d equal to NCV dt, and work done dw equal to pressure into change in volume, ଜାଣିଛନ୍ତି pdv, the work done. So the first law and second law is connected with this expression. And third law of thermodynamics. Third law of thermodynamics states that, now another thing I forget to write here, what is the how the entropy of the universe changes. Now entropy of the universe always increases because universe is an irreversible process. reversible नुहे, आमे पुणी मूल को फेरी जाऊ नांती, तेणु since universe is an irreversible process, then universe केबे to start? It starts from the explosion, big bang explosion. Okay, and we are now at this stage. So can we now return back? No. So this is irreversible process. So since it is irreversible process, its entropy increases. So inverse entropy increases. So third law of thermodynamics states that equilibrium entropies of all systems and the entropy changes in all reversible processes, reversible isothermal processes, tend to 0. Then entropy tends to 0 as temperature approaches absolute 0. This is the third law of thermodynamics. In the next unit, time is running out. Okay, cover up this unit 10, just idea about the thermodynamic potentials. When a system can be subjected to work by pressure only, there exist 4 thermodynamical potential functions, all having dimensions of energy. These 4 thermodynamic potential functions have the dimension of energy. They are internal energy, enthalpy, H equal to, you see, work done plus the internal energy, then total energy you can say. Internal energy plus work done. So total energy. PV, pressure into volume, gives you work done. If work is done at constant pressure P, suppose its volume changes by V, so total work done is PV. It gives total energy. Helmholtz free energy, again you see, F equal to U minus Ts. U is the internal energy, a T into S, ST is the heat Q, that is energy, and gives free energy is U minus Ts plus PV. That means F plus PV. F is U minus Ts. The infinitesimal changes in thermodynamic potential K U H F G. Infinitesimal changes du habo kete na TdS minus PdV. Similarly, dH hଉଛି ds plus VdP and dF equal to minus S dt minus PdV. And dG equal to minus S dt plus VdP. Okay. Now see about the four Maxwell relations. So Maxwell established from the exact differential equations, Maxwell developed the differential form of relations among the pressure, volume, temperature, entropy. So there are four equations derived by the Maxwell. They are known as Maxwell relations. Four relations. Now see, del T by del V at constant entropy. Entropy change not changes. S. When we write the subscript as S, that is the entropy is constant, equal to minus del P by del S at constant volume V. Del T by del P at constant entropy S equal to del V by del S at constant pressure P. And del S by del V at constant temperature T equal del P by del T at constant volume V. Similarly, del S by del P at temperature T equal to minus del V by del T at pressure P. Okay, we have three TdS equations relate changes in entropy to change in temperature, volume, and pressure. TdS equations, so which relating to change in entropy, which relate କରୁଛି change in entropy to change in temperature, volume, pressure. TdS equal to NCV dt plus T del P by del TV TV. Similarly, another TdS equation is TdS equal to NCP dt minus T del by del T P dV. Third TdS equation is NCV delta T by delta P V dP plus NCP del T by del V P dV. And energy equations we specify the variation of internal energy with volume and pressure, that is equal to del U by del Vt equal to T del P by del Tv minus P. So, okay, and Joule Thomson coefficient, Joule mu equal to delta T by delta P equal to 1 by Cp 2a RT minus B equal to B by Cp Ti by, if you take B here common, so this is B by Cp, it is 2a by B, it is 1, so 2a by Rb, that is Ti by T minus 1. This Ti is known as in temperature of inversion of the gas, temperature of inversion of the gas. That means every gas undergo Joule thermal expansion at a temperature below inversion temperature. If below temperature of the gas becomes the inversion temperature, then T equal to Ti. So that becomes 1, there will be no expansion. So below inversion expansion, so Joule Thomson expansion takes place below inversion temperature. Okay. With this, we conclude the today's class.
ସାର୍ ସେ ଯୋଉ ଲିଙ୍କରେ ଆପଣ କହିଥିଲେ ଷ୍ଟଡି ମେଟେରିଆଲ ସର୍ଚ୍ଚ କରିବା ପାଇଁ ସେଥିରେ ଆଉ ସବୁ ଆସୁଛି କିନ୍ତୁ ଫିଜିକ୍ସର ଆସୁନି।
ଆସୁନି କେମିତି? ବିପି ଯୋଉ ଜ୍ଞାନ କୋଷ?
ଆଜ୍ଞା ସାର୍, ଇ ଜ୍ଞାନ କୋଷରେ ମାରିଲି କେମିଷ୍ଟ୍ରିର ଆସିଲା କିନ୍ତୁ ଫିଜିକ୍ସର 135 ଆସୁନି। ପୂର୍ବ ଗୁଡାକ ସବୁ ଆସୁଛି ଫାଷ୍ଟ ଇୟର ର।
ତ ଗୋଟେ କାମ କିଛି ବ୍ୟସ୍ତ ହୁଅନି। ମୁଁ ଅଲରେଡି 4ଟା ଯାକ ଡାଉନଲୋଡ କରିଦେଇଛି।
ଆଜ୍ଞା।
ହେଲା ଏଟା ଯେତେବେଳେ ସରିଯିବ ମୁଁ ସବୁ ଯାକ ପଠେଇଦେବି। ନହେଲେ ଗୋଟେ ତମେ ମେଲ ଦବ, ତମେ ସମସ୍ତଙ୍କ ମେଲ ଦେଲେ ମୁଁ ସେଟାକୁ ପଠେଇଦେବି। ହେଲା।
ଆଜ୍ଞା ଠିକ ଅଛି।
ଆଜି ଏଇଠି କନକ୍ଲୁଡ କରିବା। କଣ ହଉଛି କି ୟୁ ସି ଏ ଯୋଉ ଡେରିଭେସନ ଗୁଡାକ ଅଛି, ଆମେ ଗୋଟାଏ ଯଦି ଡେରିଭେସନ କରିବା ଗୋଟାଏ କ୍ଲାସ, ମୁଁ ତମକୁ 3ଟା ୟୁନିଟ୍ ପାଇଁ କି ହିଣ୍ଟସ ଦେଲି। ନାଉ ସି ୟୁ ଗେଭ୍ ସମ୍ ଆଇଡିଆଜ। ଯଦି ଆମେ ଯଦି ଡେରିଭେସନ ଭିତରେ ରହିବା, ମାତ୍ର 2ଟା ଡେରିଭେସନ କରିଲା ବେଳକୁ ଆମକୁ ସରିଯାଇଥାଏ। ବଟ ଦି ପ୍ରସେସ କଣ ହଉଛି, ଗୋଟେ ବ୍ଲକ କୁ ଗୋଟେ କ୍ଲାସ ରେ ଆମେ ସାରିବା। That is why it is very difficult. Another thing, another unit was written, that is the radiation unit, black body radiation, ସେଠି Planck's law, Rayleigh's law, Wien's law, ଏ ବିଷୟରେ Stephen's law, এই ବିଷୟରେ ଖାଲି କହିଥାଏ। ଏଇ ତ ଟାଇମ ହେଇଗଲା ବର୍ତ୍ତମାନ ସୁଦ୍ଧା ଆମ ପାଖାପାଖି ଆମେ ଘଣ୍ଟେ 15 ମିନିଟରେ ଗଲେଣି। ୟା ପରେ ଆଉ ଜଣେ ଆଉ ଗୋଟେ ଆସ୍ପଦ ଥିବ ଜଏନ ଇଏ କରିବା ପାଇଁ କରେଇବେ। ସୋ ଟିକେ 1 ମିନିଟ ରୁହ, କଥା ହବା।